always place the strength or the area of the impulse next to it. This is not the height of the impulse. The height of the impulse is what? Infinity. So, one of the cardinal properties of the impulse is that when it's integrated over an interval that includes where it is present or it's active, you get 1. So actually it doesn't even matter if I change this to minus epsilon to plus epsilon, as long as the interval I'm integrating over includes 0. Stopping at 0 is going to give you a meaningless result. Okay? You always have to cover it. Suppose I have a function x of x, and it's got a plot. And at the origin, x is continuous. Okay, so it doesn't have any pathological features at the location I'm interested in, or in some neighborhood of 0. I count this with the non-ideal impulse. Non-ideal impulse has with delta as height 1 over delta. We call this delta, set the cap delta, t. It's centered around 0, and it's got a width delta and a height that's inversely proportional to its width. So the area under this non-ideal impulse is 1. Now, if you multiply x of t with delta delta of t, if x is continuous in this neighborhood of 0, specifically at 0, and if delta is sufficiently narrow, can you give me an estimate of what you're going to get? I want to plot the pointwise product of this red box and this white curve. What do I get? All the actions taking place around 0. Can you give me an approximation? X at 0. So let's say x at 0 is this value here. X at 0. I haven't taken limits yet. I'm just assuming this is sufficiently narrow, and I want to come up with an approximation to that product. If you don't want to approximate, what is it going to look like? You're active here, right? From delta over 2 to minus delta over 2. You've got flat times this curve here. What kind of a shape am I going to have? Shape of the curve. And let's say that's the curve. Okay? So that's exact. If you want to approximate, what would you do? What did you do in calculus when you studied integration? Well, strips, right? So if you were to approximate, this would be at what height? I'm picking this point as the point of approximation. If this is sufficiently narrow, x is continuous at 0. It doesn't vary a whole lot in that small neighborhood of 0. So what's this height? x0 over delta. Okay? Now what delta is of x t delta t dt. Can you give me an approximate value for this? What's the area of this rectangle? No? X of 0. Because the width is delta times x0 over delta. The delta is canceling, you're left with x of 0. Okay, so this is an approximation as long as this strip has non-zero width. Now, if you take the limit as delta goes to 0, of this left-hand side, you're going to get exactly x of 0. But when you take the limit as delta goes to 0, that delta sub delta approaches what? Huh? No, it approaches what function? The direct delta. So this is where we get the identity xt delta t dt is x0. In fact, you can change these limits to include any interval that includes where the delta is active. In general, we do it this way. When the delta comes in contact with a function that happens to be continuous at the location where the delta is active, and you place it inside an integral, you get the value of the function at that location of activity of the delta. This property is called the sifting property. Of the Dirac delta. We didn't have to go through all these gymnastics when we talked about the Kronecker delta. In discrete time, the story was very straightforward. Because you have a lollipop of height 1, and you put it in a summation, and it pick up the value. Not a problem. We didn't have to do all these limiting cases and all these shenanigans. But with the continuous language, we have to. More generally, if I have a function that's continuous at t naught, when it comes in contact with a Dirac delta at t naught and you integrate, you pick up the value of the function at t naught. And it's kind of straightforward to see also graphically. So you've got your function x, and you pound it with an impulse at t naught of strength 1. What's the product of these two? If you want, you can go back to that story. Look at that picture and see what happens when you take delta to 0. What happens when you take this delta to 0? What is this shape going to resemble? Huh? When I take this delta to 0, the height goes to what? The width goes to what? 0. So I'm going to have an impulse. I know I'm going to have an impulse at 0. At t0. But what's the area of that impulse? It's no longer 1. X of t0. assuming x is continuous at t0, this is the same thing as saying I have scaled the impulse by x t0. This is an identity. It's another one of the characteristic equations that govern the Dirac delta. And this is called the sampling property. Again, this property was very easy to see in discrete time because you had an impulse, a lollipop, multiplying the signal. Obviously, it's going to pick up the value of the signal where the lollipop is present. Yeah?
How is the sampling property different from the simpling property?
They're very much related. You can grab that from this.
And even though there we're getting x0 instead of 1.
Yeah. Yeah. So what this says is whenever you pound the signal with an impulse, you get an impulse at the location of the original impulse, but now the strength of the impulse has changed. And the strength of the impulse is now the value of x, the signal, at that location. Okay? Now the Dirac delta, technically speaking, is not a function. It falls under a class of objects called generalized functions. In applied mathematics textbooks, you will see them referred to as distribution functions, generalized functions, and so on. And if you want to get into their properties, you'll get drowned out. As far as we're concerned in this class, we don't really care about what the Dirac delta is. All we care about is what it does and how it behaves when it comes in contact with another signal, either in this form or inside an interval. Okay. Continuous time unit step. The unit step is another one of those functions that we'll make use of quite frequently. Did you know that with u in this class? And because of the discontinuity, there's no unique way of describing it. We'll stick with this in this class. T greater than or equal to 0 is 1, is 0 for t less than 0. Some textbooks leave out this equality sign. Technically speaking, that's problematic. Why? Because if this is to be a function, it's got to tell me what it's going to do to every element in its domain. And to skirt that issue, we'll just put an equality sign. For all intents and purposes, when we apply a function like this to a system, it doesn't matter what its exact value is at 0. Sometimes it may be more useful to define it this way. 1/2 at t equals 0, 0 for t less than 0. If you apply these two to a given system, let's say we have Meatball's clunker. We apply the gas pedal. So there's no gas pedal pressure at time equals 0. You go and you stay constant. Whether at exactly time equal to 0, the value is 1/2 or 1, it won't make any difference in terms of the behavior of the system. Systems respond to areas under the force, areas under the signals. We developed that story when I first started talking about strongly keyed functions last week. So, but we'll stick with this definition in this class. So suppose you have, so we're talking about the unit step. Just as we had special relationships between this signal from minus infinity to t. You can see the problem arising at t equals 0. What happens when you integrate from minus infinity to some value t? T is less than 0, what happens? You get 0. If t is greater than 0, what happens? 1. And we'll take our liberties and put that equality sign. So, this, of course, is the unit step. So we now established that the integral of the impulse from minus infinity to t is the unit step. What does that say about the about the impulse in terms of the unit step? Derivative. There's one more comment before we break. Notice what's happening. The impulse is the derivative of this function. So I'm coming along, it's flat, the derivative is 0. Okay? I hit the discontinuity. I get an impulse because the derivative is infinity. That's what the impulse is. It's infinite. That's 0. The strength of the impulse is the jump in the discontinuity. So, if you have a signal that's like that, discontinuous, and you take the derivative at t equals 0, let's say there's a jump A, discontinuity. And let's call this a function f. So, when you differentiate f, I don't care what happens here, I don't care what happens after t naught. Right now. Don't care. Don't care. At t naught, I'm going to have an impulse. So this is a tool that we've now gained. We can now differentiate functions with discontinuities using the Dirac delta. I'm going to get an impulse at t naught, and the strength of this impulse is A. Now you can have it. summarize what we've done so far. We've got the Dirac delta, which you can define to be active at any point. The Dirac delta, just like the Kronecker delta, is active when its argument is 0. Just remember that. That's how you figure out where it is. When the argument of the delta is 0, that's when it's active. So the argument is 0 and t, the dummy variable, is equal to t naught. So when t is equal to t naught, that's where you have the arrow. Its strength or area is 1. This Dirac delta enables you to give non-zero area to a point. The point being t0, and this Dirac delta enables you to give an area to that point. If you had a function that was 0 everywhere except 1, like that, what would be the area at t0? 0. This is the kind of function you've seen before. So this is a new beast. It enables you to give area to a countable set of points, in this case, a point with 0. It's got a sampling property. So when you multiply it by a function that's continuous at the location where it's active, you get a scaled impulse. And when you integrate, let's say from minus infinity to infinity, or it doesn't have to be that, it has to be some neighborhood of t naught. Then from the, so this is the sampling point, sampling. And this is the sifting property. You can get the result here by looking at the sampling property. X times the shifted delta is X evaluated at the location where the delta is active, times delta t minus t naught dt. Well, this x t naught is a constant now. It has no t dependence anymore. So I can pull it outside the integral. And I'm left with the integral from minus infinity to infinity of this shifted impulse. And what is that? 1. And so you get your sifting property, which is integral xt delta t minus t naught dt is equal to x t naught. The unit step is the integral from minus infinity to t of the Dirac delta, which means the Dirac delta is the derivative of the unit step. Now just, yeah.
Is that going to be e tau?
Yes. Now in discrete time we had the ramp function. So too you can define a whole family of functions here related to the impulse and the unit step. So if you take the unit step, u of tau. And you integrate from minus infinity to t, what kind of a function are you going to get? Integrate less than 0, what do you get? 0. So 0 when t is less than 0. And what happens when t is greater than 0? I haven't drawn the height properly. This height is supposed to be 1. You get what? T. For t greater than or equal to 0. And what does this function look like? What does that function look like? Let me hand this. Ramp. That's exactly what it is. So a ramp that starts at 0. So you can also say the unit step is the derivative of the ramp. When you differentiate the ramp, you get 0, all the way up to 0. And then suddenly it jumps to a slope of 1. And that's why the value of the unit step is 1. So there's a whole family of these. If you integrate this, you'll get a quadratic curve, and so on. But the most useful ones are the unit step, the impulse, and sometimes the derivative of the impulse, which is called the delta. I won't get into that, at least not now. So the way to survive the Dirac delta is to just think of the two main properties, the sampling and the sifting. And if you're ever in doubt, go back to the original drawing of the non-ideal delta and justify those two properties by taking the limit of this story as delta goes to 0, capital delta goes to 0. x of t. Right? This is at 0. Okay. I'm multiplying this by an impulse at where? At 1. And so what value does it pick up? So this is, let's say, 1. Where is this?
0.
Well, the value is 0, but at what time does that occur? No. The cosine curve. Where does it cross 0? When is the cosine equal to 0? That cosine. The first time after time equals to 0. When does it reach 0? When the argument is what? You're getting nervous for no reason.
I don't understand what you're asking.
I want you to plot this function. When you plot this function, you get this wave, right? Forget the impulse for now. Let's not talk about the impulse. I'm plotting a simple cosine function. Okay? Cosine goes above 0 and below 0. And at some points, it crosses 0. Where is this first crossing point? At what value of time? When the argument is pi over 2, which is 2. So, when I want to draw the delta at 1, I need this so I can figure out what orientation this arrow has with respect to the first 0 crossing. Is it after the first 0 crossing or before? Okay, so that's why I'm asking the question. So now we have this arrow of strength 1, and I'm multiplying it by x of t. What do I get if I were to redraw this whole? What's the product? So let's change that to cosine pi over 4t. Okay? What do I get? What kind of shape? What do you get when you pointwise multiply this function with this arrow? What happens at all locations other than 1? 0. And at 1, what do you get? Well, what kind of a shape? Is it this? Cosine of pi over 4? What is it? Let's go back here. What happens when I multiply the red arrow with the function? What kind of a shape did I get? It's at a point, but what? How do you represent the value of the product at that point? With a circle or with an arrow? With an arrow. Oh. All right. So we got an arrow. And what is the area under this arrow? Cosine pi over 4, which is root 2 over 2. Okay? And that's at 1. Okay. Now what happens when I integrate that product? When I integrate this product from minus infinity to infinity. Cosine pi over 4t delta t minus 1 dt. What do I get?
You get the value of that?
Exactly. You get the value of this function where this impulse is active. This impulse is active at t equals 1. That's when the argument of the delta is 0. So you plug in t equals 1, and that's the value. And that's root 2 over 2. Okay? Let's do one more example. I want to make sure we Now, it's important that you get fluent with this because you're going to be using these properties left, right, and center. After this example, we'll take another break. So let's say I'm integrating from minus infinity to delta t minus t naught e to the I omega naught t. What do you get? This is some function of time. It's coming in contact with a shifted impulse. This function of time is continuous, so I'm not worried about any pathological situations occurring at t naught. What's the value of this interval? Totally important. E to the I omega naught t naught. And so if I ask you what this is, what will you tell me? Because it's this function evaluated at t equals 0, which is 1. You'll use this a lot later on. Okay, let's take a break, and then I'm going to move into a discussion of systems and their various properties. Finally, I once put up a description of systems, namely as functions that map the domain to a range, where the domain is a space of input signals, or a set of input signals, and the range is the output signal space. And I can visually various functions. So each of these xi's or xl's, x sub 1, x sub 2, x sub 3, is a function in its entirety. So x1t will have some expression, x2t will have some expression, and so on. When I don't use the t in there, I'm referring to the signal in its entirety. And so the system takes an input signal and maps it to an output signal. Because f is a function, it can't map the same input signal to two different output signals. But it can map two different input signals to the same output signal. Yeah, essentially, it's exactly what a function would be. Yeah. So here, f is mapping x1 to y1. Okay? I can't have an f that maps x1 to y1 and also maps it to y2, because that would violate the definition of a function. But I can have a system that takes two different input signals and maps them to the same output signal. That's possible because a function can do that. What makes systems more complicated than signals is their domain and range. That's what makes them more complicated. When you look at one signal, x1 would be, say, let's say I'm talking about a continuous time signal. It maps the reals to either the real or the complex, for example. Okay? And you can plot it. This would be your x1 of t. So when I say x1, I'm looking at this whole object. When I say x1 of t, I'm looking at a particular t. That value right there. And you need to make this distinction, and the book is very clear about what that distinction is. So a signal takes, say, the set of reals, or the integers if it's a discrete time signal, and maps it to the reals or complex value quantities. And you can plot it, at least when it's real. Systems take entire sets of these functions and map them to elements in the space of such functions. So we use a different notation for systems. So when we say x is from reals to reals, this would be, for example, a real value, continuous time signal. Okay? If I say x is from reals to complex, then it would be a complex value, continuous time signal. Again, it doesn't have to be time. This can be space. If I'm measuring the thickness along the pipe or a rod, then this won't be time, this will be space. If I say x is from the integers to the reals, then I'm talking about a real value, discrete time signal. And the same for complex value, discrete time signal. Similarly defined. Complex value. Okay? So, a signal is a function. It has a domain and a range. A system, too, is a function. Go to the next word. A system is a function. So there's an arrow. Now, if I'm talking about a system that takes real value continuous time signals, I would put that these square brackets. And let's say it spits out a real value continuous time signal. This notation is the same as saying the set of all signals x such that x is continuous time and real value. In plain English, set of all continuous time real value signals. And you can use your imagination and think of all the other permutations in this story. So this is a system that takes real value continuous time signals and maps them to real value continuous time signals. Okay? Clearly, this set is more complicated than just the set of reals. And that's what makes analysis of systems a little bit more interesting. Now, I don't want us to get hung up on terminology and lingo. Okay, in this class, we'll be talking about continuous time systems, discrete time systems. Continuous time signals, discrete time signals. And the signals are either complex values or real values. That's basically the landscape that we'll be living in. What I want to dive into is the set of system properties. System properties. The first, and these are all idealizations of the real world. The first of which is linearity. You've already seen this in your physics courses. A system that's linear is a system that satisfies the superposition principle. So, satisfies superposition. I'll give you an example. Suppose I have a voltage source, and I hook it up to a resistor. And I use as the output, so this is my input signal. And this is my output signal. From your physics class, can you tell me how y is related to x? So this resistor now becomes a system. I have a system now. What that? X, y. Y is a function of x. And I also represent y at its instantaneous value by writing f of x at time t. These are all notations. This represents the entirety of the relationship between the two. So it says x viewed as an entire signal is fed into this function, and this signal pops out. This one gives their instantaneous relationship. So, can you tell me what the relationship is between this output signal, which is the current, and the input voltage? Y is equal to x over r. Right? simultaneous relationship y of t is equal to x of t over r. Now what happens if I have two voltage sources? What's the response then? Can you think of these two as one merged voltage source? So let's think of the two of these as one merged voltage source. And x will be related to x1 and x2 in what way? x1 plus x2. This is potential, electric potential. So you go, it's like going up a height. You go from ground level to some height, and then you take more stairs, you go to another height. So you've got x1 plus x2. Now I can draw two figures. Oops. R, where I say the corresponding response for x1 is y1, and the corresponding response for x2 is y2. Can you tell me what the response y is to the combined sources? y1 plus y2. In other words, this is equal to x1 plus x2 divided by r, which is x over r. And in your physics courses, to figure out how two different sources would affect the behavior of the system, you would zero one out, figure out what the response is corresponding to the other one. Then you would zero the other one out, figure out what the response is to the first guy, and then you would combine them. That was the principle of superposition you've seen in physics. And that's exactly what it is here. So the resistor with this model is an example of what we call a linear system. A linear system has two properties. So x goes in, y comes out. Y is equal to f of x. If I multiply the input signal by a constant, I didn't go over this in that example, then what happens to the response? Alpha times what? This is called the scaling property. In the resistor example, it would correspond to, for example, doubling this voltage, which would result in a doubled current. That's the scaling property. Now, suppose an input signal x1 produces an output signal y1, and an input signal x2 produces an output signal y2, then if the system is such that its response to x1 plus x2 is y1 plus y2, like in the resistor example, then we say that the system is additive. It satisfies the additivity property. The system is linear. If it satisfies the scaling and additivity preference. I.e. superposition. And you can also have a shorthand for this. If x1 produces y1, x2 produces y2, if alpha 1 x1 plus alpha 2 x2 produce alpha 1 y1 plus alpha 2 y2 for all constants alpha 1 and alpha 2 and all input signals x1 and x2, then the system is linear. It's not a very sophisticated or complicated property, but it's very useful. And there are hardly any systems in the real world that are linear. But we model them a lot of times as being linear. When you model a system as being linear, the analysis becomes much more tractable. So to the extent that your approximation is reasonable, you get reasonable results from your analysis. Let me give you an example. Let's look at modulation. You've already seen this, where we take a signal and pointwise multiply it by another signal. Okay? My question to you is this system linear? This is my system. It takes x as its input and spits out y, and here the diagram shows the instantaneous relationships, the relationship between the two. So y of t is x of t, f of t. My question is this linear? Talk to your neighbors for a minute or two and let me know. Jason. Okay, is it scaling? That's usually an easier one to check. So what happens when you scale the signal x? So let me define a new signal x hat, which is alpha times x. So x hat is going in. What is the system f do to it? Multiplies it by f of t. So y hat is x hat multiplied by f of t. The question is this equal to alpha times the original response, alpha y? So that's the question mark. You've scaled the input, and feel free to use the hat trick lavishly. The corresponding output, what the system does is, whatever signal you give it, it's going to multiply it by f, pointwise. So that's what it's done. It's saying, now I'm giving it x hat. The system's not going to care what I call this signal, x or x hat. You can call it whatever you want. It says, I'm going to multiply it by f of t, pointwise. So I take x hat, which is what you're giving me, and I'm going to multiply it pointwise by x. The question is this equal to alpha times what? And how do you conclude that it does? That it is? Yeah. activity. So this, and if I send an x1 into the system, what do I get? y1, which is x1 of t times f of t. And the same for x2. Now what happens when I send in x tilde of t, which is x1 of t plus x2 of t? I send that into the system. What is the system going to do to it? Yeah, so y tilde, the corresponding response, will be x tilde times f. And you sub in for x tilde, which is x1 of t plus x2 of t times f. And it's not hard to see that this is simply equal to x1 f plus x2 f. This is y1 and this is y2. Okay, we'll pick up next time.